So welcome to the basic thermodynamics class. So topic is a chapter 1, fundamentals of thermodynamics and perfect gas laws. So in this class we'll solve some numerical problems based on the perfect gas laws. Perfect gas laws. So in the previous class, we discussed about the Joule's law, Avogadro's number, specific heat at constant volume, specific heat at constant pressure, and relation between specific heats, ratio of a specific heats. So before solving the problems based on the perfect gas laws, so in the last class we will discuss about the Avogadro's law. So Avogadro's law states that what is the Avogadro's law states that so the equal number of equal volumes of all the gases means a perfect gases under the same conditions, and same conditions means the temperature and the pressure contain equal number of molecules, contains equal number of molecules. That means, so how you define the Avogadro's law means Avogadro's law states that equal volumes of all the perfect gases under the same conditions of temperature and pressure contain equal number of molecules, contains equal number of molecules. So if you consider mkg of a gas whose molecular weight am, then you can write as the number of kilomoles is obtained by equation n is equal to m divided by capital M. So in that we can write n is equal to 1 means m is equal to capital M. So that is not a kilogram mole. That means that the kilogram mole, what is the definition of kilogram mole means 1 kilogram mole of a substance is the amount of that substance in kilograms. So you are taking is a kilogram mole. That means that the amount of substance in kilograms is numerically equal to the molecular weight. So molecular weight. So molecular weight of oxygen is a O2. We can write as a 32. Like this, hydrogen 2 is the molecular weight. It follows the Avogadro's law. The volume occupied by a 1 kg of a mole is same for all the gases at the same temperature and pressure. At same temperature and pressure. So by using the characteristic gas equation, we can find the Avogadro's number. In that also one definition is also there, but that is a molar volume. Molar volume is nothing but the product of the molecular weight and the specific volume is called molar volume. Product of the molecular weight and specific volume is called molar volume. From using the characteristic gas equation, we find that an Avogadro's number, that is 6 into 10 to the power of 23 molecules at NTP conditions. Here that the NTP condition is important. So what is the, how will you get this 6 into 10 to the power of 23 molecules means 1 kg mole of any perfect gas occupies the volume of 22.4 meter cube and contains 6 into 10 to the power of 23 molecules at NTP conditions. So the number 6 into 10 to the power of 23 is called Avogadro's number. So what is an Avogadro number? Means the 6 into 10 to the power of 23 is called an Avogadro's number. So next coming to the Joule's law. Next coming to the Joule's law. So what's that Joule's law is next? Joule's law. Coming to the Joule's law. Joule's law is nothing but the internal energy is directly proportional to the temperature. Directly proportional to the temperature, and it is independent on the pressure and volume. So Joule's law states that internal energy of a gas is a function of temperature only, and it is independent on pressure and volume. We can write as a du directly proportional to dt. We can write as a du is equal to Cv dt, because here taking as a volume as a constant, that's why du Cv dt. Du is equal to change in internal energy, dt is equal to change in temperature, Cv is a specific heat at constant volume. So we all know that the specific heat at constant volume and specific heat at constant pressure. So the amount of the heat raised by keeping volume as a constant at 1 degrees Kelvin is called a specific heat at constant volume. Next, the amount of the heat liberated at 1 degree Kelvin, 1 Kelvin, maintaining with the constant pressure is called the specific heat at constant pressure, and we denoted by the letter C suffix P. So, the relation between specific heats. So, what is the relation between two specific heats Cp and Cv? So, with a gas constant R, we can write as a R is equal to Cp by Cv. For the problems, it is a very important. R is equal to Cp minus Cv, and adiabatic index is a ratio of specific heats, means adiabatic index gamma is equal to Cp by Cv. So, from the two equations, if you solve the two equations, we will get Cv is equal to R power R divided by gamma minus 1, or Cp is equal to gamma R divided by gamma minus 1. So, this is the relations between the specific heat and gas constant. So, we will solve the numerical problems on a characteristic gas equation and problems on a specific heat. So, first problem. So, the density of air at NTP is 1.29 kg per meter cube. So, here they given the density of air at a normal temperature pressure. So, they didn't given the temperature and the pressure. Simply they mentioned there is the NTP conditions. So, NTP conditions means you have to take the temperature as a 0 degree centigrade. 0 degree centigrade means it is a 273 Kelvin, and pressure 760 mm of mercury. So, in terms of kilonewton per meter square, it is a 101.321 kilonewton per meter square. Calculate the characteristic gas equation. Calculate the characteristic gas equation. Can represented with a R. Can represented with R. So, we know that PV is equal to, first write the given data and write the formula. PV is equal to RT. First I am writing the data. Density P is equal to 760 mm of mercury, or 101.325 kilonewton per meter square. Next, temperature 273 Kelvin. Density is equal to mass by volume 1.29 kg per meter cube. So here I am writing constant. According to the characteristic gas equation, PV is equal to MRT. But in the data, they didn't mention it is in a volume or the mass. Simply they given as a density. So what is the density? Density is equal to mass by volume. So I'm bringing this volume to the right hand side. So P is equal to M by V RT. P is equal to M by V RT. In the problem, if they mention that the mass and volume, so simply they will substitute the mass and volume in the characteristic gas equation. But they didn't mention anything about the mass and volume, but they given that as density value. We know that the density is equal to ratio of mass by volume. So I am writing this equation as a P is equal to mass by volume into RT. So, but in the problem what they asked R, only R value. So, M by V I am writing as a M by V as a density. I am writing this M by V as a density rho. Density rho. Density rho. Then the equation will comes. Then the equation will comes P is equal to rho RT. P rho RT. So I am writing this P is equal to density RT. A P is the pressure and rho is the density, R is the characteristic gas equation, T is the absolute temperature. In this problem they asked the R value. So R is equal to, I am writing as a P by R is equal to P by rho T. P by rho T. So the P NTP conditions, the P value is equal to 101.3, rho value 1.29 into 273. So do carefully the cross multiplication. Here the R. So I am putting R this side only and bringing this rho into T to the left side. Then the R is equal to P by rho T. So P value 101.3, rho value 1.29 into 273 Kelvin. By using the calculator, we can get the 0.2876 And units also very important, kilojoule per kg Kelvin. If you don't remember this, if you don't know or don't remember these units, simply substitute whatever the units given in the problem, substitute in the formula, we can get the units. So P is equal to Newton, kilonewton per meter square, kilonewton per meter square. Density is equal to kg per meter cube. Temperature is equal to Kelvin. And I am writing these Newton meter as a joule, and the remaining will get cancelled, and the term is for the R units is a kilojoule per kg Kelvin. Substitute all the units. What in the problem they given is a 101.3 kilonewton per meter square. This is meter cube per kg. This is Kelvin. So convert the meter cube meter square also, remaining is a meter only. So Newton meter, kilo Newton meter divided by kg Kelvin. So I am writing this Newton meter as a joule. So unit is a kilojoule per kg Kelvin. So the characteristic gas constant R value is 0.2876 kilojoule per kg Kelvin. Next problem. A certain perfect gas exerts at 40 degrees centigrade and a pressure of 110.3 kilopascals. If the value of the gas constant is 0.26 kilojoule per kg Kelvin, find the specific volume. So in the problem what they given, a certain perfect gas exerts at 40 degrees centigrade. It is a 40 degrees centigrade, 40 degrees centigrade, and the pressure is 110.3 kilopascals. So pressure is, if the value of the gas constant, so value of the gas constant means they given as a R value C. This is C. Find the specific volume. So first write the given data. Pressure 110.3 kilopascals. Temperature 40 plus 273. In the problem they given as a degree centigrade. You have to convert into the Kelvin. 40 plus 273 is equal to 313 Kelvin. 313 Kelvin. Next, gas constant R is equal to 0.26 kilojoule per kg Kelvin. So these are the data given in the problem, and they asked to calculate the specific volume. So specific volume is denoting with a small v. So specific volume is nothing but the volume by mass. Volume by mass is equal to question mark. So according to the characteristic gas equation, PV is equal to MRT. PV is equal to MRT. So in the problem they asked to calculate the specific volume. So before substituting all the values, I am bringing these M to the left hand side. So it becomes PV by M is equal to RT by P. I am bringing this P to the right hand side and M to the left hand side. It becomes V by M is equal to RT by P. V by M is equal to RT by P. So substituting the R value, T value and P value. R value, what is the R value? 0.26 kilojoule per kg Kelvin. T value 313 Kelvin. Pressure 110 kilopascal. 110 into 10 to the power of 110.3 Newton. Kilo means kilo, Pascal, Newton, meter square. Substitute all the units in the formula. So I am writing this joule as a Newton meter. So I will get Newton cancel. Meter into meter square, meter cube. Kelvin get cancelled. So remaining is a meter cube per kg. Meter cube per kg. This is the specific volume of the given gas. So how will you find the units means, just I will tell. So I am writing the units only here, equal to, what is the formula? RT divided by P. So what is the units of the R? R units are the kilojoule per kg Kelvin. Kilojoule per kilojoule divided by kg divided by kg Kelvin. kg, capital K, Kelvin, into temperature. Sir, temperature units are Kelvin. Temperature units are Kelvin, capital K, divided by P, divided by P, divided by P. So what is the P units? Kilopascal, kilopascal, P, kilopascal. Pascal means Newton per meter square, Newton per meter square. Newton divided by, per means it is a division, per square. So here I am writing this joule as a Newton meter. I am writing this joule as a Newton meter. So I am removing this joule and writing as a 1 joule is nothing but the 1 Newton meter. 1 Newton meter. 1 Newton meter. So first I am cancelling this Kelvin and this Kelvin, and next kilo and numerator kilo, next is in Newton and in denominator also and Newton, and it is in a denominator. So these go to the upside. So already one m is there. So m into m comes as a meter cube. M into m is as a meter cube. M into m is a meter cube. This m into meter square. This meter square is in a denominator. In denominator also it is present in denominator. So it goes to the numerator. Meter into, remaining terms are meter into meter square per kg. Meter into meter square per kg. So it is nothing but the meter cube per kg. So the unit of the specific volume is meter cube per kg. So this is the way how to find the units also. So this is the way you can write this as a meter cube. M into meter square is nothing but the meter cube per kg. So in the problem they given that the temperature, pressure and the R value. Simply they asked to calculate the specific volume. So I am writing this, the pressure is equal to 110.3 kilopascals, temperature 40 plus 273, 313 Kelvin, R value 0.26 kilojoule per kg Kelvin, specific volume. Specific volume is nothing but V by M, capital V by M. So according to the characteristic gas equation, we know that PV is equal to MRT. So V by M is equal to RT by P. So R value 0.26 into T value, temperature how much? 313. 313, P value 110.3 kilo. So I am substituting with values of same units also. So units also I am substituting here. So I get the units as a meter cube per kg. So answer is 0.738 meter cube per kg. The specific volume of a given gas is 0.738 meter cube per kg. So move to the next problem. For a certain ideal gas, R value, characteristic gas constant value R, they given R value 0.278 kilojoule per kg Kelvin and gamma is equal to 1.25. Gamma is equal to 1.25. Determine the Cp and Cv value. Determine Cp and Cv and molecular weight. Determine Cp, Cv and molecular weight. So R value, gamma value they given. First write the R value, next gamma value, Cp question mark, Cv question mark, molecular weight we are denoting with capital M question mark. So according to the relation between specific heat and the specific heat ratio value, we know that Cp by Cv is equal to gamma, Cp minus Cv is equal to R. By using the two relations, we know that Cv is equal to R divided by gamma minus 1, So R value 0.278, gamma value 1.25 minus 1. So calculating we will get 1.112 kilojoule per kg, 1.112 kilojoule per kg. Here the units also, if you don't remember if you don't know the units, simply substitute in the formula. So here the gamma is a constant value, so whatever the units for the R, that are the units of the CV only. So 1.12 kilojoule per kg Kelvin. Next, here the kg Kelvin, I missed that Kelvin. Here is there a kg Kelvin. So CV is equal to 1.112 kilojoule per kg Kelvin. Next, on the CP value, we can find the CP value in two ways also. If you can directly substitute, the CP is equal to R gamma by gamma minus 1, or CP minus CV is equal to R, or CP by CV is equal to gamma. So by using these three relations, we can find the CP value. Now I am using only specific heat ratios value. Gamma is equal to CP by CV. They given the gamma value 1.25. By using the formula R pi gamma minus 1, we got the 1.12. So CP, here I am writing the CP is equal to, I am taking this CV into the left hand side. It becomes CV into gamma is equal to CP, or CP is equal to gamma CV, gamma CV. CP is equal to gamma CV. So we know that the gamma value is a 1.25, CV value 1.112 kilojoule per kg Kelvin. So it is 1.25 into 1 minus. So CP is equal to 1.4. Gamma into CP is 1.25 into 1.12, and gamma value, CP value is 1.4. So while telling that relation between CP, CV, gamma, I told that one point also, CP is always greater than the CV. So if you want to the check answer, it will get correct or wrong, please check. Here find that the CP value is more than that of the CV value. CP is greater than that of the CV value. CP is 1.4, CV is 1.112 kilojoule per kg Kelvin. Next, we know that Ru is equal to m into molecular weight of the gas into characteristic gas constant R value. So we want m molecular weight. To find molecular weight, m is equal to Ru by R. So we know that Ru value 8.314, R value 0.278. So molecular weight is 30. So how you calculate the molecular weight means, we know that the Ru is equal to m into R. Universal gas constant Ru is equal to the product of a molecular weight of the gas into characteristic gas constant R. So we want the molecular weight. Previously we calculate the R value. Now we want the M value. M is equal to Ru by R. So we will get the molecular weight as a 30. Molecular weight 30. So going to the next problem. Here, the value of the adiabatic index of certain gas is 1.41 and its specific heat at constant volume is 0.65 kilojoule per kg Kelvin. Determine gas constant. So I am reading the question once again. Here they given that the adiabatic index. So what is, we denoted the adiabatic index with as a gamma. Gamma is 1.41 and its specific heat at constant volume, so CV is equal to 0.65 kilojoule per kg Kelvin. Determine the R value. Gas constant means R value. So first write given data. So adiabatic index gamma is equal to 1.41. Specific heat at gas constant value CV is equal to 0.65 kilojoule per kg Kelvin. We know that CV is equal to R power gamma minus 1. So R is equal to, so there is a gas constant R value. So R is equal to, I am taking this denominator, R divided by gamma minus 1. This is, so I am taking this gamma minus 1, cross multiplying that, it will move to the left side. It becomes a R is equal to CV into gamma minus 1. CV into gamma minus 1. So what is the CV value? 0.65. Gamma value 1.41 minus 1. So substitute the given data in the above relations and we will get the gas constant value. So here also how will you get the units? So here is a gamma no unit. So CV is only there. So R is equal to CV1. So whatever the units for the CV, the units of the R is also same. R is equal to 0.65 into 1.41 minus 1 is the 0.26 kilojoule per kg Kelvin. R is equal to 0.26 kilojoule per kg Kelvin. Next problem. An ideal gas is expanded from 400 kilonewton per meter square at 0.04 meter cube to 120 kilonewton per meter square and 0.1 meter cube. So they given that the initial temperature, initial volume, initial pressure and initial to final pressure and final volume. Next, the temperature fell down during this process was observed 150 degrees centigrade. If the values of Cp and Cv are 1.025 kilojoule per kg Kelvin and 0.726 kilojoule per kg Kelvin respectively, find first change in internal energy, next the mass of the gas. So first write the given data. P1 they will give the initial and final conditions. So P1 400, P2 120. Next V1, V2, volume V1 and volume V2. T1, V2. Next T1 temperature difference they given. It's a fell down to. So what T1 minus T2 is equal to 150 degrees centigrade. Cp value and Cv value. So this is the given data they given. P1, P2, V1, V2 and temperature difference Cp and Cv value. So first we have to calculate change in internal energy dU. Next mass of the gas. So first we have to calculate the change in internal energy dU means first we have to calculate the R value. So we know the relation between the gas constant and the specific heat is equal to R is equal to Cp minus Cv. So R is equal to Cp minus Cv. So what is the R value here? 1.025 minus 0.726 is equal to 0.3. So R is nothing but Cp minus Cv is equal to 1.025 minus 0.726 is 0.3. Next, applying the gas equation at state 1. So P1 V1 is equal to mRT1. So they asked to calculate the mass. So P1 V1 is equal to mRT1. At state 2 P2 V2 is equal to mRT2. So from equations 1 and 2 we can write as a P1 V1 minus P2 V2 because we don't know the T1 and T2 as a directly because I am writing this equation P1 V1 minus P2 V2 is equal to MR T1 minus T2. So we can substitute all the data in this equation. After that we will get the M value. So we know P1 value, V1 value, P2 value, V2 value and we have to calculate only M value. We know that the R value also 0.3 and difference in the temperature. So M is equal to P1 V1 minus P2 V2 by R T1 minus T2. So P1 value 400, V1 value 0.04 minus P2 120 into 0.1 divided by 0.3 into 150. So it will get as a 0.089 kg. This is the mass of the given gas. So first write the given data. First write the given data, read the question carefully, write the given data and in the first problem they ask the give a mass. So how will you get the mass by using the given data? So by you know that the ideal gas equation P1 V1 is equal to mRT1 and at the second stage P2 is equal to mRT2. So I am separating, they give you the temperature difference. So I am writing the two equations 2 minus 1 1 minus 2 P1 V1 minus P2 V2 is equal to MR is here, the MR is a common MR T1 minus T2. So we want only M value. So I'm writing M is equal to P1 V1 minus P2 V2 by R into T1 minus T2. So substituting all the values, whatever given in the problem, substitute all the values in the formula, we will get the M is equal to 0.089 kg. And in the problem they also asked about to calculate the internal energy D MCV T2 minus T1, MCV T2 minus T1. So in the first we calculate the mass CV value given in the problem T2 minus T1. So in the problem they given as a T1 minus T2 as a difference 150, but here the formula is T2 minus T1. So we are writing as a minus 150. So du is it minus 9.75 kilojoule. So internal energy is decreasing. Internal energy is decreasing. So we know that at constant volume du is equal to mcv T2 minus T1. So in the problem they given the T1 minus T2 value as a 150, but in the problem it is a T2 minus T1. So I am writing as a minus 150. So we will get the answer in negative minus 9.705 kilojoules. So next, a gas having initial pressure, volume and temperature as a 275 kilonewton per meter square, 0.09 meter cube and 185 degrees respectively. So what is the given here? Gas having initial pressure, volume and temperature. So P1, V1 and T1, 275 kilonewton per meter square, 0.09 meter cube and 185 degrees centigrade respectively, is compressed at a constant pressure until its temperature is 15 degrees centigrade. Calculate the amount of heat transferred and work done during the process. And they given this R value and CP value also. So if you know these two values, automatically we know the CV value and gamma value also. So what is the relation between the specific heats and the gas constant is Cp minus Cv is equal to R. Cp minus Cv is equal to R. Given data and calculate the whatever as in the problem. Calculate the amount of heat transferred and the work done during the process. So dq and dw have to calculate. Data P1 275 kilonewton per meter square. Here I am converting the kilo as a, I am writing this kilo in terms of a 10 power 3. So it is 275 into 10 power 3 Newton per meter square. Next, volume V1 0.09 meter cube. Next, temperature we have to convert into the absolute temperature, that is a 185 degrees centigrade they given that. So I am converting these degrees centigrade into absolute temperature by adding this a 273. So T1 is equal to 185 plus 273 is a 458 Kelvin. So this is the initial conditions they given in the problem. Next, final conditions also. T2 15 plus 273, it is a 288 Kelvin. 288 Kelvin. Next, R value 290 kilojoule per kg Kelvin. Next, Cp value 1.005 kilojoule per kg Kelvin. So this is the data given in the problem. So they asked to calculate the dq and the work done. First, to find the mass of the gas. How will you find the mass of the gas? By using the equation P1V1 is equal to mRT1. By using the characteristic gas equation P1V1 is equal to mRT1. So how to calculate the mass? So M is equal to, so bring this RT1 into the left side, it becomes in the denominator. So M is equal to P1V1 divided by RT1. M is equal to P1 V1 divided by RT1. So what is the P value? P1 value given 275 into 10 to the power of 3. 275 into 10 to the power of 3 and V value as a 0.09 and R value 290 and T value 458 Kelvin. 458 Kelvin. So observe that write all the values in the formula and we'll calculate that. We will get as a 0.186 kg. 186 kg. Next, we have to calculate the amount of heat transferred. So Q is equal to mCp T2 minus T1. mCp T2 minus T1. So m value 0.186 here not equal to, it is in a bracket. It is in a bracket. Sorry, into. It is an into 0.186 into 1.005 into T2 minus T1. T2 minus T1 means T2 is given 288, T1 as a 458. So after calculating we will get as a minus value is a minus 31.78 kilojoules. Next, so what is the negative sign indicates? Here the negative sign indicates the heat has been extracted from the gas during the process. So we have to write this also. So this became the negative value. Negative means that the sign indicates that the heat has been extracted from the gas during the process. So how will you calculate this one? Again I am telling how to calculate the Q value. So before in the problem they asked to calculate the heat transfer. So heat transfer formula is a mCp T2 minus T1. mCp T2 minus T1. So we know from the data we know the Cp value, T1 value and T2 value, but we don't know the m value. So how will you first you have to calculate the m value. So how will you calculate the m value? So by using the characteristic gas equation, that is PV is equal to mRT. PV is equal to mRT. In the problem they are given that is an initial conditions. Initial conditions means we have to take P1 V1 is equal to MRT1. MRT1. So, but what do you want? M is equal to PV by RT. M is equal to PV by RT. So first condition M is equal to P1 V1 by RT1. So substitute all the values in that P1 V1 by RT1, we will get the M value. So after getting the M value, Q is equal to mCp T2 minus T1. So M value 0.186, Cp value 1.005 and T2 minus T1 288 minus 458. It is minus 31.78 kilojoules. So it's a negative sign. We got the negative sign. So what the negative sign indicates that the heat has been extracted from the gas during the process. So next, so work done. We know that the work done is equal to P V2 minus V1. So we know only the V1 value. Before getting the V1 value, before calculating that work done, we have to calculate the V2 value. So V2 is equal to at constant pressure. They mentioned that. So V is directly proportional to the temperature. So V1 T1 is equal to V2 T2. V2 T2. V1 by T1 is equal to V2 by T2. So V2 is equal to V1 into T2 by T1. So substituting all the values, we will get the V2 value. So we know that the work done during the process is P V2 minus P1. So they given the P value and we calculate the V2 value, and in the problem they given the value, they given the V1 value. So from this we will get the work done. So work done also will get the negative value. It is a minus 9350 joules. Here also I am writing this joule as a kilojoules. It is a minus 9.53. So negative sign we will got this. Next problem. A certain gas has Cp value and Cv value. Cp value 1.965 kilojoule per kg Kelvin and Cv value 1.5 kilojoule per kg Kelvin. Find its molecular mass and gas constant. So molecular mass is M value, gas constant is R value. Take Ru as a 8.315 kilojoule per kg mole Kelvin, kg mole Kelvin. So first write given data. So Cp value is 1.965 kilojoule per kg Kelvin. Cv 1.5 kilojoule per kg Kelvin. Molecular mass M question mark, gas constant R question mark. Next, we know that Cp minus Cv is equal to R. So by using these two values, we can get that R value. So 1.965 minus 1.5 is equal to R. So by using the calculator, do the 1.965 minus 1.5, will get the R value as a 0.465 kilojoule per kg Kelvin. So units are also same. So it is a minus. Is whatever the units for the Cp and Cv, the units of the R is also same. So we got the R value as a 0.465 kilojoule per kg Kelvin. So next, coming to the universal gas constant, Ru is equal to m into R. Ru is equal to m into R. So we given in the data Ru value and we got the value of R. So we want to calculate the molecular mass M. Molecular mass M. So we want to calculate M. So M is equal to, we are writing Ru by R. So we are bringing this R to the left hand side, it becomes M is equal to Ru by R. So 8.315 into is equal to M into 0.46, it is 18. 18. So molecular mass is equal to 18 and gas constant will get as a R value. So next problem. Oxygen occupies a volume of 22.4 meter cube per kg mole at NTP condition. Find the universal gas constant and characteristic gas constant value. So here they given the gas as a oxygen. Till now they mentioned what is the gas. Here they mentioned is an oxygen. So oxygen formula is O2 and the molecular weight of the oxygen is a 32. Occupies a volume of 22.4 meter cube. So volume B is equal to 22.4 meter cube per kg mole at NTP. Find its universal gas constant and characteristic gas constant. So what is the universal gas constant? We are representing with R suffix U and characteristic gas constant as a R. And they mentioned it is also NTP conditions. NTP conditions is nothing but the temperature at 0 degree centigrade. So 0 degree centigrade, it is in a Kelvin, 273 Kelvin, and the pressure is a 760 mm of mercury. So we can write the 760 mm of mercury as a 101.325 kilonewton per meter square. Kilonewton per meter square. So I am first writing the given data. At NTP conditions, the pressure 760 mm of mercury. I am writing as a 101.325 kilonewton per meter square. So same at normal temperature and pressure, value pressure is 760 mm of mercury, so 101.325 kilonewton per meter square. And we have to write the temperature also. What is the temperature? Is a 0 degree centigrade and we are converting 0 degree centigrade into the Kelvin by adding the 273. It becomes a 273 Kelvin. Next, volume V. Volume V is equal to 22.4 meter cube per kg mole. 22.4. They given as the molecular volume. They given the molecular volume. So that is V suffix mole is as a 22.4 meter cube per kg mole. So characteristic gas equation, PV molecule is equal to RUT. PV molecule into molar is equal to Ru into T. So in the problem they given the V volume, V molar, Ru, how to calculate the Ru value, and we know the pressure and temperature values. So I am writing that Ru is equal to P molar volume by T. P into molar volume by T. It is 101.325 into 224 by 273. So by calculating that we will get 8.314 kilojoule per kg mole. So here also how to write the units I will tell. So you know the formula P molar volume by temperature. So here I am writing that the units only. So what is the units of the pressure? Kilo Newton per meter square. Kilo Newton per meter square. Kilo Newton per meter square. So meter square is in denominator. Kilo Newton per meter square. Next, molar volume. They given that per kg mole, meter cube meter cube per kg means divided by kg mole. kg mole. kg mole. kg mole divided by this one mole divided by temperature. Temperature means Kelvin. So temperature is Kelvin. So this is kilo. So here I am cancelling this meter square and this meter cube into as a meter. So remaining is only meter. So I am writing this meter cube into meter square into meter. So 1 meter is there. One is there. And the Newton meter. So it becomes as a Newton meter. I am writing this Newton meter. 1 joule is equal to 1 joule is equal to 1 Newton meter. So divided by kg mole Kelvin. So kilojoule. This K. So this K is a kilo. This K is a Kelvin. So this here Newton meter. So and this writing Newton meter as a joule. So in numerator is a kilojoule divided by kg mole and Kelvin is also in denominator. So the units of the RU is a kilojoule per kg mole Kelvin. And they asked about this one is a universal gas constant. Next, coming to the characteristic gas constant. So what is the characteristic gas? How will you get the characteristic gas constant? So we know that RU is equal to M into R. So we want only the R value. I am writing this R is equal to R is equal to RU by M, where M is the molecular weight. So what is the gas they given here is an oxygen. So oxygen means represented with the O2, O suffix 2, O2. So RU value we got as a 8.314 kilojoule per kg mole Kelvin. So R is equal to RU by M. So 8.314 is nothing but the 0.26 kilojoule per kg Kelvin. So this is the universal gas constant value and the characteristic gas constant value. So RU is equal to 8.314 kilojoule per kg Kelvin. So in this class we discussed about the problems on the characteristic gas equation and the problems on specific heat. In the next class also we will solve the problems on the first unit thermodynamics system and the perfect gas equation. Tomorrow we will conclude the first chapter. Thank you.